All right, folks, I think we're just about ready to get started. So if you wouldn't mind taking your seats, and we're gonna get started with the session right away here. So this will be the security session, in which we implicitly admonish you to pay more attention to security, like you all know you should be doing, but maybe you don't. So the first paper in this session is going to be called Lightweight Non-Invasive User Authentication on Earables, and it's going to be presented by the lead author, Chang Shuo, who is currently a research engineer at the School of Computing and Innovation Systems in Singapore Management University. His research interests rotate around mobile computing and mobile wearable healthcare. Recently, he is particularly centered on human activities monitoring with wearable technology, and he is currently seeking a PhD position. So I will let you have the floor.
Okay, uh, this is my first presentation, so I'm quite nervous now. But anyway, just go it. Hello everyone, my name is Chang Shuo. I'm currently a research engineer in Singapore Management University. Today I'm happy to present our work, Lightweight and Non-Invasive User Authentication on Earables, which is co-authored with Xiao Dong from Singapore Management University and Dr. Ting Dang from University of Cambridge. Earables refers to wearables that can be worn on or inside ears, such as earbuds or hearing aids, which has been more and more popular in recent years. Major technology companies like Apple and Samsung continue to introduce different types and versions of earbuds, and this trend seems still unstoppable. And the earbud market is still growing, and with the Gartner saying that the earbuds have already constituted nearly half of the wearable market by 2022. When used with a mobile phone, earbuds can keep the phone unlocked and recommend music genres or personalized acoustic features based on the user's wearing habits. If the earbuds can recognize the user's identity, this feature may become more even advanced and offer additional services. The most conventional method should be the speech-based method, which relies on the unique vocal feature and skull structure of the user. The in-ear microphone records the bone and tissue contact sounds that can capture the skull structure, and the out-ear microphone can record the eye contact sounds that can capture the vocal feature. But they require extra human effort and may be affected by external noise. Another approach is probing-based, which rely on the unique geometry of user's ear canal. The probing-based method transmits the audible or inaudible chirps to capture the unique geometry of each individual's ear canal, which can be used to identify the users. But it requires actively transmission and complex processing pipeline, increasing the computing overhead. And moreover, the transmission of audible chirps may be unpleasant for users. And now some commercial earbuds, such as Huawei earbuds, has a bone conductor sensor to detect the difference in bone vibrations, which is caused by the user's unique skull structure when they're speaking. However, they also require users to speak, and introducing an extra sensor will increase the cost and need a more dedicated circuit design. So here we present our lightweight and non-invasive authentication approach. The lightweight means we don't need actively transmit any probing signal, and the non-invasive means we don't need to require user to speak. Our method combines the use of in-ear and out-ear microphone to detect the unique shape of each person's ear canal, which is used to differentiate users' identity. And this figure shows the principle. When there is a noise, the noise enters our ear canal and eventually reaches our eardrum and cochlea. However, when our ears is obstructed by an earbud, a closed chamber is formed between the earbuds and eardrum, and most external sound will be blocked outside. We use the out-ear microphone to collect this environmental noise. When the remaining noise enters our ear canal, it gets trapped in this chamber and reflects inside your ear canal. And moreover, this chamber amplifies the lower frequency components of the noise, which can be easily captured by in-ear microphone. So in summary, the unique shapes of ear canal create different occluded chambers and modulate the in-ear sound signal, and finally result in the different ear canal transfer function. So we built a prototype to validate our idea. Basically, we print an earbud with a 3D printer, placing the out-ear microphone at the end of the handle of the earbud, and another microphone near the ear tip facing inward to collect the in-ear sound. Then we connect the earbud with a Beta Mini board and an audio codec for recording the data. Here we have an example of the sounds collected by the in-ear and out-ear microphone in 3 different scenarios, which are the human singing, man singing, and traffic sound. Look at the time domain first. The blue signal is the out-ear signal, and the orange one is the in-ear sound. You can see that the in-ear microphone generally receives a lower amplitude signal than the out-ear microphone because the earbuds block part of external sound. And in frequency domain, you can see that there is a clear energy reduction in the high frequency bands for all 3 scenarios. This is due to the occlusion of the ear canal, suppressing the high frequency band. On the other hand, the closed ear canal chamber also amplifies the lower frequency, so that the energy loss due to the earbuds obstruction is compensated to some extent. Based on this observation, we can conclude that there is a mapping between the in-ear and out-ear sounds at a different frequency bands, which is due to the modulation of the occluded ear canal. We hypothesize that if the scaling factors are distinct for different peoples and consistent for the same person, the in-ear and out-ear mapping could be utilized as a unique feature for our authentications. There are 2 phases in our system. During the enrollment, the user is asked to wear the earbuds and record some environmental sounds. We first segment our data into 1-second samples, and since the frequency range of most environmental sound is below 4 kHz, we downsample the out-ear and in-ear signal to 8 kHz to reduce the computing overhead. Then signal is converted to frequency domain using FFT. Because the environmental sounds may not have the strong energy in all the frequency band, we only select the frequency band with acceptable energy based on the out-ear signal. And finally, the selected out-ear and in-ear pairs are used to calculate the ear canal transfer function with the linear regression. During the authentication phase, we collect both in-ear and out-ear environmental sounds and do similar pre-processing and energy detection. Then we use the individual's ear canal transfer function to convert the out-ear signal into its in-ear modulated version. And the modulated version is compared with the real in-ear signal. If there is a high similarity, the authentication is accepted, and vice versa. This figure shows the correlation between in-ear and out-ear sounds energy. This is clear that the mapping between the in-ear and out-ear is almost linear for each frequency band. And to understand whether the ear canal transfer function is salient enough to capture the difference in ear canal geometry, we conduct 2 experiments. First, we can see that for the same subject, the scaling factor curves are more consistent, which indicate a high intra-subject similarity. And then for different subjects, the scaling curves are more distinguishable, indicating a high inter-subject dissimilarity. We recruit 12 subjects for data collection and select 6 common environmental sounds that cover different frequency bands. Then we ask each subject to wear our prototype while a laptop playing each environmental sound for 2 minutes. We split our data into 70% training, 10% validation, and 20% testing. We use 3 metrics: false acceptance rate, false rejection rate, and their mean value balance error rate to evaluate our approach. After splitting the data, we iteratively treat one subject as the legitimate one, and the rest are imposters. First, we can say that the error rate of validation and test are most equivalent, which means our approach can be generalized to unseen user. And second, we design a voting strategy that calculates the major results within 3 continuously segmentations. The performance can be further improved with this strategy, which is comparable to other complex approaches. And this figure shows the error rates of each individual. We can see that the performance varies among subjects, which is possible due to the ear canal transfer function of some subjects having higher similarity with others. So this is harder to distinguish them. Because our work relies on the background noise to map ear canal transfer function, the performance may be affected by different type of noise. To understand this effect, we calculate the error rate of each noise type. We can see that the different noise types have varying performance depending on the property of the noise. For example, air conditioning, traffic, and restaurant noise are relatively stable over time, so the scaling factors are more reliable, while the volume of the songs and ocean waves may change over time, resulting in a big energy change in certain frequency bands and therefore the poor performance. We measure the latency and energy consumption of two platforms, RISC-V and Arduino. The authentication can be finished in 10 milliseconds on RISC-V, indicating our lightweight system and ensuring a real-time operation. Moreover, RISC-V and Arduino are general development boards without optimization, so the consumption will further reduce with well-designed microcontroller and circuits. Our approach relies on the frequency mapping between in-ear and out-ear sounds, so this only exists when the ear canal is well sealed. However, users may wear the earbuds in many different ways in daily life and affecting the sealing. We conduct an experiment with 3 tightness levels, which are tight, normal, and loose. This result suggests that wearing the earbuds too tight will not affect the performance, but a losing fit will result in a higher error rate. And moreover, our system needs a relatively strong ambient sound to map the user ear canal geometry. We're testing the authentication performance with different noise level, and we can see the system is reliable at 6 decibel and above, but untrustable at 40 decibel and below. Let's talk about the future work. First, since environmental sounds may not have high energy in all frequency bands, we plan to use the synthesized sound to collect more fine-grained data to find a better transfer function. We also plan to explore the correlation between frequency components and optimize the mapping between in-ear and out-ear sound. And second, we treat all frequency bands as the same weight now. In the future, we can improve the authentication performance by paying more attention to specific frequency bands that are more sensitive to human ears, such as 2 kHz to 5 kHz. And we can do this by assigning different weights to different frequency bands when computing the distance, which can enhance the difference among subjects. And in summary, we propose a novel, lightweight, and non-invasive user authentication scheme for earbuds, and we demonstrate the feasibility of the purpose scheme with a balanced error rate under 5%. And finally, we assessed the power consumption and latency. And by the way, I'm seeking a PhD position. If anyone have a vacant position for a PhD student, please contact me. Much appreciated. Thanks for listening.
I'd like to open up the floor for questions, if anyone has any questions for the speaker.
Oh, hi.
Hello, thanks for your talk. And I'm Kano Xu from Peking University. And my question is the motivation. Why do we need authentication for earbuds? There are many private information in smartphones or laptops, but I'm not sure that such private information exists in earbuds?
Okay, so you talk about the motivation.
Yes.
As I say before, if the earbuds can authentication user can identity the users, we can customize personalize the feature acoustic feature for the user, or recommendate the specific music genres, and keep the phone unlocked. So it can be very a lot of applications if we can identify the users.
Okay, so you are
And
going
also the smartphone can identify the user, maybe use the heart rate, heartbeats, or some ECG signals.
So it's about identification rather than authentication.
Authentication and actually authentication is to detect if the user is the legitimate one, and authentication is to select one user from a big group. And I think both of these can lead to many applications.
Okay, thank you.
Thanks for your questions.
Thank you for the presentation. What if the ear inside changes through time?
Oh, these are good questions. Because we depend on the geometry of ear canal, which is similar to the probing-based method. And as the previous work says, the geometry of ear canal will consistent in 3 months, at least. So I think because we based the same things, the geometry of ear canal, I think the time will not affect it too much.
So the process to fingerprint the user's ear canal is fast, and
Yes.
I guess you can do it at regular intervals.
I think if you want to make a new profile, maybe it's only you use the synthesized sounds. It's only on the 30 seconds, but use the ambient sounds. Maybe it take a long time because the frequency band is not sufficient.
Okay.
Okay.
Thank you.
Thank you.
Okay, thank you very much for your talk. So yeah, I have 2 questions. The first one is which kind of microphone that you are using, like the digital one or the analog one? Because I heard that you mentioned lots of information about noise. So yeah, just curious, because using
We use an analog one.
Oh, analog one.
Yes, and the noise is most caused by the circuits, because the circuit electronic noise.
Yeah, because the digital one can reduce the noise. I would say that it will have better performance.
We only tried the analog one at this time, and maybe we can try it later.
Okay, thank you. And the second one is that about assembling brush. So you reduce I would say you reduce from 16K to 8K, right? The assembling rate of the microphone to process. Yeah. So you collect data with the default assembling rate of 16K, right?
Yes.
And then you reduce to 8K. So is it still good? You can still keep
a motion?
Yeah.
Oh, I think it's this about 2 aspects. The first aspect is the motion will affect the ceiling of the earbuds, which is can affect our performance.
Yeah.
And the second one is there is some motion artifact when you do sports or something. And this one is more like vibration, which is in low frequency. Mm-hmm. So I think if we focus on the specific frequency band, like 2 kilohertz to 5,000 kilohertz, the vibration can be filtered out.
Thank you very much.
So if you keep a good ceiling, maybe it can be used at motion status.
Okay, thank you very much.
Thank you.
Hi, Zichang from Google. Very interesting idea. So one question about experiments, maybe I missed it. Did you test it on one side, on both sides?
Oh, we only use one side.
Okay, so I'm curious, if you use both sides, how would it be helpful? And I imagine there may be 2 approaches. One
Actually, it should be some improvements.
Yeah.
And Actually, the environmental sound is like a surround sound, so it's not direction. But in our experiments, we use a laptop to play the music. So if the laptop is in front of you, it's not so big improvements with one side or both sides. So to reduce the computational overhead, we only use one side.
Okay, because I was also wondering, so like maybe you can calculate the difference between the left side on the right side, and that delta may also be some kind of a signature of a person.
Okay,
I'm just curious about that.
Okay, thank you for your recommendation.
Thank you.
All right, let's thank our speaker. Alrighty.